So in question number 6, we're going to revisit the guiding question that got us into this log situation in the first place, which was in question number 1, namely question letter E, that said, is there a known function that would have given us the exponential inverse? Remember, we started with an exponential function, y equals 2 to the x, and recognized that when we graphed its inverse, this was not a familiar function to us. We'd never seen a function with an asymptote that was kind of pointing vertically this way that curved up the way it did. So at the time, we said, no, there's no known function. There's no visible way that I could predict what this curve was. There's no way I know what the opposite of an exponential function is. But now we know that the opposite of an exponential is a log. So that, in question number 6, is the key knowledge that we need to be able to say, okay, now I can find the inverse. This is going to be the first time that you'll really see why we use a log, and it's mainly for inverse type problems. And I'll get into more detail about what that means as we get more and more exposure, but let's for now just assume for a second that we think back to what we know about inverse. Way back in Unit 4, we established that an inverse is when you switch the input and the output of a function, namely the x and the y. So the inverse of y equals 2 to the power of x would be x equals 2 to the power of y, which is mathematically correct, but not a traditional function. Traditional functions should always say y equals, and clearly y is not by itself here. So the reason why we have logs is because this technically is something for which we need to get y by itself. Y is currently trapped in an exponential expression. And y is not really something I can easily free up. I can't divide the 2 because 2 isn't multiplying the y. It's exponentiating, which is legitimately a verb, by the way. So I can't do the opposite of the 2 to get y by itself until I understand what the 2 is. If I understand what the 2 is doing, then I can understand what the opposite is to get rid of it. And again, 2 is not multiplying the y, so I can't divide. 2 is not adding the y, so I can't subtract. 2 is not squaring the y, so I can't square root. 2 is exponentiating, which means the only way I can get rid of the 2 is by using a log. The opposite of an exponential is a log. So here's what we're going to do. We're going to write the word log, and we're going to translate this problem into a log expression. Believe it or not, that will fix our issue. Let's see if we can do this. Now, if it confuses you, the fact that this is a little bit backwards compared to all the problems we've done before, you can definitely rethink of the problem as 2 to the power of y equals x, if it helps put things in a more familiar order. But hopefully you remember something really crucial, namely that the subscript is always the base of the exponential. So we know the subscript is going to be log base 2. We know that it's always log base 2 of whatever's on the opposite side, so x equals, the last part left over would be the y. And if you're like, wait, how did she do that? You can always just quickly retrace your steps. Remember, you can do the little arrow, and you can just make sure the things are in the right order. 2 to the power of y equals x. Yep, that's what this original problem said, 2 to the power of y equals x. So we know we've gotten everything that we needed, and we know that we've gotten everything in the right place. But, step back and notice, we've gotten an expression now with y by itself. That was what we were trying to do. We were trying to come up with an expression where y was by itself, and now we have one. Y equals, and I'll translate the order, log base 2 of x. They are definitely interchangeable, although some people find the little arrow thing doesn't really work for them backwards. So you can kind of switch the order of things however it makes sense to you. But what we've essentially done is establish that the inverse of an exponential is a log. The inverse of exponential 2 to the x is log base 2 of x. They are opposites of each other. And that word inverse might intrinsically want to link itself in your brain to the word opposite, which is a good thing, because inverses and opposites are what algebra is all about. We learn inverses so that we can do opposites. For example, you learned very early on in your math career that subtracting is the inverse of adding. They're opposites. So to get rid of something subtracting, you add it in an algebra problem. Then we learned that multiplying is the opposite of dividing. Then we learned that squares are the opposite of square root. And we've learned lots of pairs of opposites. So this is simply the next pair that we can start to understand. The exponential is the opposite of the log, and the log is the opposite of the exponential. They kind of go vice versa. So think of this pair of functions, the exponential and the log, as opposites of each other. And hopefully that will help you start to realize in this bottom section why logs exist. They exist so that they can be opposites for exponentials. We know that algebra is full of exponential functions, compound interest, all those different problems that you did with percent multipliers, all of those crazy details that you saw in geometric sequences that took on an exponential form. There are tons and tons and tons of exponential functions in this world. So we have to be able to solve them. And to be able to solve them, we need an opposite. To solve algebra, you have to know the opposite operation of whatever you're trying to solve. So if I'm solving something exponential, now I know I'm going to need a log to do it. In the next question, we'll revisit inverses a little bit more and make sure that we understand that this actually fits into the bigger picture of inverse that we learned in Unit 4.